Once again, here we are going to talk a little bit about the last chapter we're supposed to kind of cover. We probably won't get through everything, but we're going to hit some of the highlights, hopefully. So chemical kinetics deals with really chemical reactions and really sort of the speed of a reaction, how fast or how slow a chemical reaction sort of proceeds. There's two kind of main things that we talk about sort of in chemistry and reactions, and a lot we don't necessarily talk about here in this class, but you will if you go on to take 200B, and that is thermodynamics. And thermodynamics deals with a couple of things. One thing that we use to sort of cover in here, which is energy, like the conservation of energy and things of that nature. It also deals with things like entropy and sort of the disorder in the universe and stuff like that. So when you deal with thermodynamics, which you'll again really sort of cover in 200B, what you really are sort of looking at in those type of questions is the idea of whether or not a reaction will sort of take place. And a lot of times we use the word spontaneous when we describe that, whether a reaction will be spontaneous or non-spontaneous. And sometimes people have an idea when they hear spontaneous that they think the reaction just sort of occurs super fast, like snap your fingers and it's sort of done. And that's not necessarily the case. So if a reaction is sort of spontaneous, what it means is under those conditions, the reaction will take place. It could be really fast, could be really slow, but it's the right sort of conditions for a reaction to take place. The study of kinetics, which is what this chapter is about, really sort of answers the question of sort of how fast or slow a reaction takes place. So when we study kinetics, that's really what we're looking at is, how fast or again, even how slow a reaction may take place. When we talk about a reaction rate in terms of chemistry and chemical reactions, a lot of times what we're following is sort of the change in concentration or the change in molarity over a period of time. So a lot of times that's why we end up with these type of units for reaction rate, which is molarity over seconds. So that's really like your change in concentration over your change in time, which is basically what a rate is, right? How fast something is changing over a period of time. So in a reaction, that's sort of what we look at when we look at reaction rates. And if we look at sort of a generic reaction like A going to B here, what we would expect to happen is at the very start of this reaction, we would expect pretty much all of A needs to basically go and produce B. So at the very start of the reaction, we would expect a lot of A and pretty much no B. And as this reaction would take place, we would expect the amount of A to start to go down, and it would go down because we pretty much need our reactants to make our products. And at that point, we would also obviously start to see some products being made, and we start to see the amount of B start to increase. And we could write what is sometimes referred to as a rate expression, which is sort of what we see here on the bottom. That basically describes sort of that change that's occurring in a reaction like this. So this is the rate is equal to minus the change, which is what the delta sign means, the change in the concentration of A. And again, when you do see these brackets, this usually means concentration. And usually that is molarity, which is obviously our moles per liter is what we're looking at there, over the change in time. And when we do something like the change in concentration, it's sort of initial, final minus initial, right? So in a reaction, kind of where you end and where you start. And time obviously is final minus initial as well. Now, we do see a negative here, and that is important, and that is because A is a reactant. So we would expect, again, over time for the concentration to decrease. And because of that, we would expect that the final concentration of A actually would be lower than the initial concentration, right? So if it's decreasing over time, where you end is going to be less than what you start with. And the negative there is really important because when you do calculate the rate for a chemical reaction, these numbers here should always be positive numbers. So for example, if I started with A at the start, I had 4 molar, and at the end there I had like 2 molar. When I would calculate the change in the concentration of A, it would be 2 minus 4, which would give me minus 2 molar. And that minus there and the minus that would be in here would then turn our rate into a positive number, which is what we're looking for. We actually don't see that on the product side. On the product side, we see it sort of increasing with time. So when we end up with at the end should be more than what we started with. And it is calculated by the rate is equal to the change in concentration of B over the change in time. And again, if you look at B, for example, in a made up example, starting and ending for B, 0, and maybe you end at 4, so molar. So the change in concentration of B would be obviously 4 minus 0, which would give you positive 4 molar. So first important thing in sort of kinetics is when you do calculate the rate of reaction, it should always be a positive number. And we do incorporate that negative into the rate expression to assure that we do end up with that positive number, because the difference there for our reactant should always give us a negative concentration because it's less than what we started with. Any questions on that there? So in general here in kinetics, there's usually a lot of graphs and stuff like that that we follow, but here we can see sort of the progression of this reaction at the very beginning, A, which is the black circles there, B, which is the red circle. So you can see at the time 0, you really have no products, it's all reactants. And as the reaction is proceeding, you start to see obviously some products being made here, some red circles developing, and a majority obviously of red at the end. Graphically here, what we were kind of looking at earlier there, again, at the very beginning of the reaction, it's all reactants, no products. Obviously, as we start to make some products, we're using up our reactants. And again, we have obviously in this case, since it's a one-way street, kind of more products there than the reactants at the end. Now, visually, we oftentimes can follow a kinetics reaction by some type of visual color change that occurs. So for example, in this reaction here, Br2 is sort of this color here. And that's like the Br2 being present. All these other guys over here are actually colorless, which would be represented here. So by following the change here in the reaction, we can basically see that the reaction is definitely going to the product side there as the color starts to diminish. Because the solution does have a color, much like what we did like in our Kool-Aid experiment, we could use a very simple machine like a Spec 20 and basically follow the absorbance values over time. If you remember, right, the absorbance of a solution is dependent on the color. So the darker the color, the more absorbance you would have. Obviously, the lighter the color, less absorbance you would have. So this guy at the beginning would have a pretty high absorbance, right? And pretty much no absorbance here at the end. When we use something like that, as we've talked about when we did that experiment, basically we have a light source that shoots light at a specific wavelength, right? And the light that's being absorbed is complementary to the color that we actually see in the solution. And you always want to set your wavelength right to the maximum absorbance, which is kind of what the spectromaster person did in that experiment. And in this case, we would want to kind of set our sort of peak absorbance here somewhere in the 400 nanometer region. Again, the purpose of that is so when you take your reading for your samples, they will all be on scale. Obviously, if we set the wavelength way over here, you're not going to get it pretty much any absorbance readings or stuff like that. They're all going to be pretty much off of the scale. Now, we can relate this by something like Beer's law, which is A is equal to B times C, where this is the absorbance. That's Beer's constant, which is that proportionality constant, and the path length, and that's concentration. So you can very easily sort of follow the absorbance values of these solutions over time, and you then could use something like Beer's law to convert it into concentration values over time. And really the absorbance is proportional to the change in concentration. By simply just following that change in absorbance values, you could do a very simple sort of calculation to convert them into concentration values. And thus you could really follow how the change in the concentration is over time, basically, which is basically a kinetic sort of idea. The experiment for day is a little bit different. We're going to actually wait for like the color to appear. So you can actually wait for the color to appear. It'll be kind of colorless, and then I'll get this like bluish purple type color that will appear when the reaction is completed. So There's a couple of different types of rates that we sometimes talk about. And again, if we sort of graphically look at this, this is, again, the concentration of Br2 over time. And since this is Br2, which is a reactant, we would expect the concentration to decrease with time, which is what we do see here. You could actually find the average rate, which is basically the change in the concentration, kind of final minus initial, divided by the change in the time final minus initial. But there's also an instantaneous rate, which is really the rate for a specific period of time. So it's kind of like when you drive a car, for example, if you drove from here to Arizona or something like that, you know, along the way, maybe you're doing 65, 75, 80, 85-ish, something like that. For a specific period of time, but maybe if you average out your whole sort of trip there, you drove an average of like 70 miles per hour. But there are certain windows perhaps where you are driving maybe a little faster, maybe a little bit slower. There are certain periods of time like that. So an instantaneous rate is sort of a look at a specific, obviously, period of time, which may be different than the overall average rate from sort of beginning to end if you look at the average rate of a particular reaction. A lot of times we do sort of calculate the average rate of a particular reaction by following those sort of rules. You could also calculate sort of the instantaneous rate by taking the slope of the tangent, which we won't do in this class, but that's sort of what you could do in that case. Now, there is sort of a relationship that is a constant relationship when we do look at a reaction overall. And what we do see is that the rate for specific periods of time, they do very much vary as the reaction is progressing, but there is sort of a relationship of the rate constant, which is little k here. So little k is the rate constant. And it kind of tells you how fast or slow sort of a reaction is taking place. It is little k, as again, if you take 200B, you will know capital K is the equilibrium constant, which is different in a sense. So here in kinetics is little k, which is the rate constant. And we could write something like this guy right here, which is also sometimes referred to as a rate law. And that is the rate is equal to k. K is the rate constant times the concentration, in this case, of Br2. And if we actually solve for the rate constant, we actually get this number here, which we can see in the table is a constant value all the way through. So the relationship of sort of the rate to the concentration of our reactants does give us this sort of linear relationship, and also basically a very much a constant value for each of these for a particular reaction. It is obviously dependent on the temperature and the reactants that are taking place for that particular reaction. Now, sometimes when we are doing kinetics experiments, and a lot of times we do deal with solutions. So following something like the change in the absorbance value over time, which you could relate to the change in concentration over time, is a very easy way to do that. But not all reactions, for example, do produce anything, things with color, for example, or colored type of solutions. So this is all colorless stuff here, even though it's kind of yellow for display purposes here in the picture. But here we're actually generating a gas in this particular case. And since this case, the gas is being generated, a lot of times it's easy to follow sort of the pressure that's changing over a period of time. And we can use our ideal gas law here to help us basically do that. We saw this when we talked about gases in a couple of chapters, but if we take PV equals nRT, and again, solve for N over V, that would be P over RT. And once again, N over V is moles per liter, which is basically the molarity. So by following the pressure in this situation where we're basically collecting a gas, we could actually relate it back through calculation into the molarity and how the concentration is changing over a period of time. We could do that because if we ran this experiment, the temperature would be held constant, and R is a gas constant, which means really the only thing you need to follow here is the change in pressure, and that can be easily done by an apparatus such as we see here that's attached. So you can basically follow the change in pressure over the change in time, which then would relate to basically the change in concentration over time. So this gives you another way, maybe if you're not, again, sort of using a solution or have a solution that has color, would use some type of absorbance value, you could do that. In this particular reaction, we could do that, and we know that pretty much the only gas there is oxygen gas, which is a product, which means that if we have any type of pressure, that means we have made some products, right? And it's all going to be a result of the oxygen gas that was developed there. So let's talk a little bit about stoichiometry. When we do kinetics, we also do need to take into account the stoichiometry that's involved in order to sort of get the correct sort of kinetics activity out of it. So obviously in this case, if we look at this reaction here, just from stoichiometry, we know that there are 2 moles of A, right? Gives us 1 mole of B. And that once again is coming from the actual coefficients in the balanced equation. So we again can write a couple of rate expressions. As I mentioned before, these are sometimes referred to as. And for example, our A, this would be the rate is equal to negative. Again, because it's a reactant, it should be decreasing with time. So we do the negative 1 over the coefficient, which in this case is 2. So that is where the half comes from, taking 1 over the coefficient, the change in the concentration of A over the change in time. We could also write a rate expression for B, which is a product, which should be increasing with time. And we would have the rate is equal to the change in concentration of B over the change in time. And once again, here, there is no negative because it's a product. And typically the coefficient is 1 there. So that is 1 over 1, which equals 1, which is why there is no 1 over something there. It's basically 1 over 1. In general, you could write a rate expression for any reactant or product in a chemical reaction by following this same sort of process here. This would be the rate is equal to minus 1 over A, which is the coefficient there of A. Change the concentration of A over change time equals minus 1 over B. Change the concentration of B over change of time. Again, when we get to our product side here, these guys are going to be positive, so no negative signs here. But again, 1 over the concentration. What the nice thing about this is it allows you to really figure out how everybody in a chemical reaction is changing. If you pretty much just know one piece of information, if you know the overall average rate, you can figure out how everybody is changing with time. If you know how a reactant is changing with time, you can figure out how everybody else is. Or if you know how a product is changing with time, you can figure out how everybody else is. You can set them all equal to each other. You could break them apart and do them separately. Like the rate is equal to minus 1 over A, change in concentration of A over the change in time. And the rate, for example, is equal to 1 over D, the change in concentration of D over the change in time. And the nice thing about this is, like I said before, this number here and this number here are the same, which means you can essentially set up those 2 things equal to each other if you like. And if you know something about A, for example, that would allow you to figure out how D is changing with time. Once again, here, as I talked about earlier, these negatives are here important. This number here should always end up being a positive number. So you should always end up with a positive number for the overall average rate for a particular reaction. Any questions on that there? All right, so why don't you try one here, write the rate expression. Okay, so if we look at this, we could start with the rate is equal to, we'll start with our first reactant here. This would be minus basically 1 over 1, so you don't have to write it since it's 1, since the coefficient is 1. Change in concentration of CH4 over the change in time. That would equal our second reactant here, which would also be negative because it's a reactant. Here we would do 1 over the coefficient, which will take care of the stoichiometry part for you. The change in the concentration of O2 over the change in time. This would equal now our product size, which should be increasing with time. So we would not put a negative here. Again, 1 over the coefficient here is still 1. So this would be the change in the concentration of CO2 over the change in time. And lastly here, the coefficient is 1. 1 over 2, change in the concentration of H2O over the change in time. So again, this would allow you, if you knew any information, numbers about anybody here in this reaction, again, to figure out how everybody else is changing. Now, 1 over the coefficient is a very convenient way to sort of do the stoichiometry together with like the kinetics part of the calculation all in kind of one move. You can actually do in certain cases just the stoichiometry part first and then the kinetics part at the end if you want. So you could do a traditional kind of like stoichiometry problem, do the mole-to-mole relationship. But if you kind of want to do it all together, you could do the 1 over the coefficient. It sort of combos the stoichiometry with the kinetics part of the calculation. All right. So why don't we actually try one with numbers here and see what you come up with. For the reaction, given the I minus changes from 1 molar to 0.868 in the first 10 seconds, calculate the average rate for the first 10 seconds and the concentration of H plus over the concentration of time. Take a couple of minutes, see what you come up. Okay, let's take a look at this one here. So for this given reaction, the concentration of I minus changes from 1 to 0.868. So really our I minus initial is 1 molar. Our I minus final is 0.868 molar. And obviously our 10 seconds is our final time and 0 would be our initial. So since we have I minus information given to us, we could write the rate expression for I minus from the equation here, and that is the rate is equal to minus 1 over 3. Again, 1 over the coefficient here to take into account the stoichiometry. Change in the concentration of I minus over the change in time. The other thing that we're interested in is H plus. So we could also write a rate expression for that guy, which is the rate is equal to minus 1 over 2. Again, for the coefficient is still reactant. Change in the concentration of H plus over the change in time. In this particular case, we have enough information there about I minus. So we pretty much have these numbers here. So we could go into here. So the rate would equal minus 1 over 3. Again, we're going to do final minus initial here for our concentration. So that's actually the 0.868 minus 1. And obviously here, this would be 10 minus 0 seconds. That difference here is less than what we started with. So that obviously should give us a negative number, which the negative number here will turn that into a positive number for the rate, which is what we're looking for. So 0.868 minus 1 divided by 3n divided by 10 gives you a 0.0044. Unit-wise, nothing cancels, so that's molarity up on top, that's seconds on the bottom, molarity per second, and that would be our average rate for this particular reaction is basically the concentration is changing by 0.0044 molar every second. First off, any question on that part of the calculation? Now, the benefit of this is we're actually looking for as well how the concentration of H plus is changing with time, which is essentially this part right here is what we're looking for. So we know that the rate is equal to minus 1 over 2 change in concentration of H plus over the change in time. We just calculated the rate above. So we know that 0.0044 molar seconds equals minus 1 over 2 change in concentration of H plus over the change in time. If we isolate this here to stay on that side, we're actually going to multiply the 2 to the other side, but not just the 2, the negative will come along for the ride as well. So it's going to be negative 2 to the other side, and that would get us negative 0.00. Let me go also 0.868 minus 1. Gives us 0.0088 molar seconds would equal the change in the concentration of H plus over the change in time. This guy is okay to be a negative because that is how the reactant is changing over a period of time, which is negatively and becoming less. So basically every second we're dropping 0.0088 molarity off of that H plus concentration is how quickly it is changing basically over a period of time in this particular reaction. Any questions on that there? And again, we end up with a negative value here, which again makes sense because H plus is a reactant, so it should be decreasing with time. Questions on either of those there? Okay. So why don't you try this one here? If 2.4 times 10 to the 2 grams of NOBR molar mass, 109.91 grams per mole, decomposes in a 2 times 2 milliliter flask in 5 minutes, find the average rate of BR2 production and molarity. Okay, let's take a look and see how we're doing. So in this case, we're given information about NOBR. We eventually want to get to BR2. So we could really isolate our two sort of rate expressions. The rate here would equal minus 1/2, the change in concentration of NOBR over the change in time. Once again, it's a reactant, which is why it's negative, and 1 over the coefficient there, taking care of the stoichiometry part of it. We also are interested in BR2, which would be the rate is equal to the change in concentration of BR2 over the change in time. It's a product, so it should be positive. Coefficient here is 1, so 1/1 obviously does give us still 1. Since we do have information about NOBR, that is really where we're going to start our calculation here. We really don't have the concentration given to us, but we do have grams in volume, basically, and molar mass. So we could actually calculate the molarity. So to do the molarity, we would want to convert our grams into moles. So they're nice enough to give us the molar mass here. And that was 109.91 grams per mole. That's going to give us 2.4 to the 2 divided by 109.91. Going to give us 2.1836 moles of NOBR. That is basically in a 200 milliliter flask, which is basically 0.2 liters. So if I want the molarity here, I actually could just divide the moles by the 0.2 liters there, and that will get me about 10.92 molar. That is basically the decomposition of it. So that is basically the molarity of how it changed over that period of time. So that really is sort of what goes in the box here. So we can then do our rate is equal to minus 1/2, and that would be negative 10.92 molar divided by our time. Our time's in minutes, but ultimately we want seconds. So I am going to do a conversion there, and that's 300 seconds divided by 300 seconds. And once again, that is obviously the 5 minutes converted into seconds there. The purpose and reason I put the negative here is, once again, this should be a positive number, and that concentration should be changing negatively over time. So technically, if we got that number, it would be 0 minus that, and that would give us a negative. So it gives us 10.92 divided by 300 and divided by 2 gives us 0.0182 molar seconds as our rate for this particular reaction here. Now we are going to relate it to our other guy, which is the rate is equal to the change in concentration of BR2 over change in time. And that ultimately is what we're looking to solve for. We already know that it basically is a 1-to-1 relationship. So that would also be the concentration of BR2 over the change in time. So it's basically, again, we're producing in this case 0.0182 molarity per second is basically being produced as this reaction takes place. So every second we increase the concentration of BR2 by 0.0182 molar. It is a positive number because BR2 again is a product, so it should end up with a positive change over time. Any questions on that there? So rate expressions are very useful in sort of kinetics because, again, pretty much you just need one piece of information and you pretty much can determine how everybody else is changing over a period of time. It's just one piece of information, either the average overall rate or just how one reactant or one product is changing. Questions on that one there? Now, as I mentioned before, you could have done the stoichiometry separately. So at this point, you could have just did a mole-to-mole relationship and got the moles of Br2 and then kind of put that into the kinetics part of it, and you'd end up with the same answer at that point. All right, so that was what we just did. All right, so let's talk a little about some of the factors that do affect the rate of a chemical reaction, the nature of the reactants. So small molecules, small reactant molecules do tend to obviously react faster than larger ones. Gases, because they're in constant motion, have a lot of energy, definitely do react faster than liquids, which liquids obviously react faster than solids, which are just kind of sitting there, kind of needs a little help along the way to kind of kick the reaction off. Powdered solids react more than block solids. Again, sort of the surface area of your reactant being able to basically come in contact with what it's reacting with. Activity series of metals. So like we talked about when we did single replacement reactions, you know, there has to be a certain reactivity for a reaction to take place. If you remember, the activity series is kind of a list of sort of chemicals or elements. Anybody higher on the list is more reactive than anybody lower on the list, and vice versa. Lower on the list is less reactive than anybody higher on the list. Ions in solution are very reactive and tend to react really fast because frankly they're free and they're floating around and they're ready to go, and in terms of making a reaction take place. In addition, temperature is a major effect on the rate of a reaction. Typically, if we increase the temperature, that provides more energy to everybody, allows reactions to take place a lot faster, and vice versa. If you kind of throw everything on ice, you would expect the rate of the reaction to sort of slow down. Again, you're removing a lot of energy, so things aren't moving around as fast. They maybe don't have the right amount of energy for that reaction to take place. Technically, if you kind of, in a lot of cases, increase the temperature about 10 degrees Celsius, for a lot of reactions, that will typically sort of double the rate of the reaction. And there is a relationship which is known as the Arrhenius equation, which you might get to a little bit later on in this chapter, which deals with sort of that temperature and rate relationship. Another way typically we can increase a reaction rate is to add a catalyst. A catalyst is not a reactant, it's not a product. It is there really just simply to facilitate the reaction, and a lot of times occurring faster. It actually doesn't get used up either. They're typically the guys you sometimes will see like up on top of the arrow, like platinum. Maybe they put H+, which is like an acid catalyst or something like that. There are also catalysts that slow down chemical reactions, but most of the time people, when they're talking about catalysts, are talking about it in the sense of speeding up the chemical reaction. It basically finds an alternative pathway for that reaction to take place. And by doing so, it's able to occur a lot faster. And sometimes that could be something as simple as like a solid platform that allows perhaps the gases all to conjugate there in one spot. And that allows everybody to come in contact with each other a lot faster than if they were just kind of flying around trying to find each other. There are different types of catalysts. There's homogeneous catalysts, which much like a homogeneous mixture means that the catalyst and everything that's reacting, they're all in the same phases. There's also heterogeneous catalysts, which are catalysts that are in different phases than, say, the reactants that are going on. Also, concentration is a big factor in terms of reaction rate. Usually, if you have a larger concentration, you typically will have a much faster reaction. If you think about concentration, which is moles of solute per liter of solution, it is really the moles of solute that are reacting in a reaction. And if you have a large molarity, then you usually have a large amount of solute in there, which means there's a lot of guys in there ready to react. In terms of gases, the higher the pressure, the higher the concentration. So obviously the higher the pressure, also in terms of gases, a lot of times you have a smaller volume, which gets everybody near each other and again, able to react a lot quicker. So let's talk a little bit about the rate law. And the rate law is a little bit different than the rate expression that we've been talking about here in just a second ago. The rate law is basically the relationship for the concentrations of the reactants to some type of power. So first major difference in terms of a rate law versus a rate expression is the rate law is all about the reactants. So it's only the reactants involved. So you don't have any products typically in a rate law. And the rate law here is the rate is equal to K, which is again our rate constant. Where it tells us how fast it's sort of occurring. Concentration of A to the X and B to the Y. X and Y are what are referred to as orders. And X would be the order with respect to A, and B would be, or Y would be the order with respect to B. You can actually get the overall order of the reaction by adding those together. So if you add up all the orders for all the reactants, it'll give you the overall order of the reaction. The order is sort of like the proportion that's necessary to sort of facilitate that reaction, maintaining a specific rate. And they can have effects on, if you know the orders of the reactants, you could usually kind of play with the rate law and the concentrations to affect the rate of a particular reaction. One important thing is the orders are not the coefficients. So they are found experimentally. They're found experimentally here. They're not the actual coefficients in the balance equation. It's not how we get those. You actually have to experimentally determine them. So for example, let's just say we had a rate law of K is equal to A times B, right? And in this case, the order here would be 1 for A and 1 for B. The overall order here would be second order. By adding 1 and 1 gives you 2, basically, is how you get that. Now, let's say, for example, we wanted to change the concentration of B or double the concentration. So for example, in this case, let's just say originally we had the rate is equal to K and the concentration of A was 2 molar and the concentration of B was 2 molar. Taking out K, which is a constant, we end up with basically 4, we'll call it molar seconds, right? When we multiply them. Let's say we decided we want to double the concentration of B in this particular case. The rate here would equal K times 2, and if we double B, it would be 4 molar. And what we would end up with is a rate of about 8 molar seconds. So in this particular rate law, the way it is with the order for A and B both being 1 in this particular case, if we double B, we basically will double the rate of the reaction. So if we were doing this type of experiment and we wanted to increase this reaction and make it occur a lot quicker, we would double the concentration of B here, and that would obviously achieve that. Vice versa here, if you want to slow it down, you could cut the concentration, right, of B or A in this case, either one actually, and it would actually slow down the reaction. Let's say we had the same guys, but we had a different rate law where the rate is equal to K times A times B to the second order. In this case, the overall order would be third order. By adding basically 2 and 1 together gives you 3, which is third order reaction. Now in this case, if we had the same concentration as we did in the previous one where each of them was 2 molar, the rate that we would get in this particular case would be 2 squared, which is 4 times 2, which would be 8 molar. So in a direct comparison of this experiment or that reaction to this reaction, having the concentrations the same, we actually have a, twice as fast to begin with. Now, in this case, if we doubled the concentration of B, we would end up with the rate is equal to K times 2 molar times 4 molar squared. That is 16, right? 4 squared times 2 is 32 molar seconds. So a much more dramatic change in the rate of this particular reaction than the first one by doing the same thing, just doubling the concentration of B. In this case, the rate goes up by 4-fold, right, from where it started. So by just simply doubling the concentration of B in this particular reaction, we could actually increase the rate 4-fold and make it occur 4 times as fast by playing with it. Same idea here. If we wanted to slow it down, we also could cut the concentration and we could slow it down. And this is sometimes very useful if you're doing some type of kinetics experiment and you're trying to do measurements and like the thing is over before you even get a chance to take a measurement. At a place where I teach, they do a lot of kinetics experiments, and sometimes when students are mixing the solutions together, by the time they mix it and they finally get it into the machine, the reaction is done, because it's a very quick reaction. So, you know, sometimes you might want to slow it down to give yourself a little bit more time to be able to actually get some measurements and stuff like that. So this is sort of what the rate law allows you to figure out and sort of determine and use. And that's sort of what the orders sort of are, you know, sort of the proportion of what you need to maintain a certain rate of each of those reactants. Any questions on that there? So since the rate law is found experimentally in kinetics problems, these are typically the type of tables that you will come across. And you'll have a reaction such as the one we're looking at here, where F2 plus 2ClO2 goes to our product here. And you'll have a sort of a table like this, basically different experiments that were performed, where you have different concentrations of your reactants and basically the initial rates that were determined. So basically the molarity per second overall for this reaction. And you could use tables like this to determine the actual rate law. Again, because the orders are found experimentally, you'll typically have a table like this. Now, some people could look at the table and figure it out, but most people, mathematical approach is maybe a better approach to do. And mathematically, we could take the rate 2 over the rate 1 is equal to K times A to the X, B to the Y, K, A to the X, and B to the Y. So what the rate 2 and rate 1 is, it doesn't mean you go to the table and take the first and second one, but you actually just go to the table and you take 2 entries. And when you go to the table to do this, what you're looking for is to basically find one entry or 2 entries where one of the concentrations stayed the same and one of them varies, in a case where you have 2 reactants. The purpose of that is so you do not end up with too many unknowns, right? It makes it a little bit hard to solve if you have a lot of unknowns. So if we start with this one generically here, the rate law would be the rate is equal to K times F2 to the X and ClO2 to the Y. Again, we don't know what X and Y is. We're going to try to use this table to help us determine it. When I look at the table and I look at F2, I see that entry number 1 and number 2, the concentration remains the same, while the concentration of this ClO2 changes. And that's sort of what I'm looking for. So if I take number 1 and number 2 from the table, and what I'm going to do is basically put all the information for one of the entries up on top and all the information for one of the entries on the bottom, to make yourself get sort of nicer numbers, a little bit more whole numbers. I would personally look at the rate and take the larger rate value and put that guy up on top and do the smaller one on the bottom. It doesn't really matter, but sometimes I'll give you better whole numbers to do it. So in this case, I'm going to put number 2 up on top. And what I mean by that, I'm just going to take all the information from the table, 4.8 times 10 to the minus 3 molar seconds is my rate. It's equal to K times the concentration for number 2, which is 0.1 for our F2. And the concentration for number 2 there is 0.04 molar for our ClO2. So all that information came from this entry right here in the table and just kind of put it into there. We're then going to do the exact same thing, except that we're going to take all the information from entry number 1 and put it on the bottom. And that would give me 1.2 times 10 to the minus 3 equals K 0.1 to the X and 0.01 to the Y. Any questions on that? So again, on the bottom, all the information from the table from number 1, up on top, all the information for number 2. Now we can do a little bit of math work here. So if I divide these 2 guys, that is going to give me a 4. When I come to the right-hand side, that is the rate constant up on top. That is the rate constant on the bottom. Although I do not know what the number is at this particular point, it is a constant, which means it should be the same number up on top and bottom. And if it's the same number up on top and bottom, they will cancel. So those guys cancel out, basically equals 1. This is 0.1 to the X divided by 0.1 to the X. Again, at this point, I do not know what the X value is, but I do know it should be the same in this reaction for both of them, which means essentially these guys are the same as well. So these guys will also cancel out completely. Now, when I divide the last thing that's left there, 0.04 divided by 0.01, that gives me a 4 to the y when I do this guy here. So that's a 4 to the y right there. At this point, you could probably figure out what y is. Y is equal to 1 in this case. By the way, if it wasn't a pretty number like that, you could take the natural log of both sides and divide is a good way to do that. So you can take the natural log of 4 and divide it by the natural log of 4, which will equal 1. But you basically can take the natural log of both sides and divide. So what we just calculated here is the order with respect to ClO2 is going to be first order. Now that we did that, we want to go back to the table. And since we kept F2 constant previously, we now want to vary F2 and find a place where the ClO2 remains constant. So if I look at the table, the F2 is changing in 1 and 3, but it does remain constant for our other reactant in 1 and 3. So we're going to do the exact same thing for 1 and 3 here. Once again, I'm going to put the larger rate up on top. So I'm going to go with number 3 up on top. So 2.4 times 10 to the minus 3 is equal to K times 0.2 to the X, 0.01 to the Y. So once again, all that information is from number 3 in the table. I'm going to divide it by all the information from number 1 in the table, which would be 1.2 times 10 to the minus 3, K, 0.1 to the X, and 0.01 to the Y. Once again, we're going to do a little dividing here. So that is going to give me a 2. Once again, the K's are going to equal each other, so they will cancel. 0.2 divided by 0.1 gives me 2 to the X. And again, this guy is going to completely cancel out at the end there. In this case, once again, it's probably easy to see that X is equal to 1 in this case. First off, any questions on that there? Now that we have the orders for each reactant, we actually could write the completed rate law. And the completed rate law in this case would be the rate is equal to K times F2 times ClO2, where each of those guys are basically to the order of 1. The overall order of this reaction would then be 1 plus 1 is second order. Any questions on that there? Now that we actually have the completed rate law and the actual orders for each of those, we now could actually use the completed rate law and that table to basically find the value of the rate constant at this point. So at this point, we could then go back and actually solve for the value of the rate constant. And to do that, what we would do is we would take our completed rate law. Some of this here, I got some right. So we would take our completed rate law and we actually would solve for K. And if we solve for K from our completed rate law, it would equal the rate is divided by the concentration of F2 times the concentration of ClO2. And again, that's just found by rearranging this rate law on the bottom here, dividing the concentration on the other side. Where do I get those numbers? I get those numbers from the table. I could choose any entry I like. I could choose entry number 1, entry number 2, entry number 3. You just can't mix and match. You could choose either one. They all should give you the same because it's a rate constant. So it all should be a constant number no matter what experiment you choose. So I'm just going to put the information from number 1 in there. And that would give me that the rate is 1.2 times 10 to the minus 3 molar seconds divided by the concentration F2, which is 0.1 molar times our 0.01 molar. That is going to give me 1.2 to the minus 3 divided by 0.1 divided by 0.01. Gives me a 1.2 as my rate constant. In terms of units, molarity up on top and molarity on the bottom will cancel. It actually gives me 1 over molar seconds. are sometimes m-1 s-1 is how it's sort of written. And again, you could have chose the entry number 2 or entry number 3. It should give you, again, the same number no matter which one that you choose from. So this is typically how we experimentally determine a rate law, is by doing multiple sort of kinetics experiments where we really keep the concentration of one of the reactants constant and vary the other one, and vice versa. And we can sort of experimentally determine the orders of the reactants, and then afterwards you have your rate law. You could use it to determine the actual value of the rate constant. Any questions by that? And by the way, as we'll see in this chapter, these units are actually the correct units that we typically see for a overall second order reaction, or typically those type of units. Any questions on that? All right, so why don't you try one here in a second. So as I mentioned before, rate laws are always determined experimentally. So you once again will always be given pretty much tables, just like we saw. Always only the reactants involved, no products in a rate law. And again, you do need to determine the orders from that table. And as we can see here, the order was 1 for ClO2, but the coefficient there was 2. So it is not found from the coefficient. All right. So the rate equation for a reaction is the rate is equal to KNO times O3. The rate is 6.6 times 10 to the minus 5 when the concentration of NO is 1/6 and O3 is 3 times 10 to the minus 6. What is the rate constant? So in this case, they actually gave us the rate law. So really in this case, we're just solving for the rate constant, which is this guy. So once again, we would divide the concentrations to the other side, and that would give us something like this. And in this particular problem, they were nice enough to give us all these values here. So we'll just plug it in. The rate was 6.60 times 10 to the minus 5 molar seconds, divided by our NO concentration, which is 1 times 10 to the minus 6 molar, and our O3 concentration, 3 times 10 to the minus 6 molar. Once again, the molarity on top and bottom will cancel, and we will end up with 6.6 to the minus 5 divided by 1 to the minus 6 and divided by 3 to the minus 6. Gives us a rate constant of 2.2 times 10 to the 7. 1 over molar seconds. If I got that right there, if I counted the right number of zeros there, I think I did. That is a very large rate constant, which means this reaction would occur pretty quick. And once again, we see the overall order here is actually 1 and 1. So the overall order is second order by adding those guys together. And we see for the rate constant, the same units as we saw previously, 1 over molar seconds. Any questions on that one there? Okay, why don't you try a table 1 here? All right. So determine the rate law and the value of the rate constant based on this information here. So see what you come up with. So we want to determine the rate law with the proper orders, and then what the value of the rate. Okay, let's take a look, see how we're doing here. So once again, we're looking for the rate law. So we can start with kind of like a generic rate law, which is the rate is equal to K, again, times our reactants here to the X and our I minus here to the Y. Really, the goal here of using this table is to figure out what these orders are. And we want to do that by, again, keeping one of the concentrations constant while varying the other. And we could do that for I minus by taking 1 and 2 here. So if we look at experiments 1 and 2, I'm going to put the larger sort of rate up on top, which would be number 1s. So that would be 2.2 times 10 to the minus 4 is equal to K times 0.08 to the X, 0.034 to the Y. And again, that's just all of experiment 1's information up on top. We're going to do all of experiment 2's information on the bottom. 1.1 times 10 to the minus 4 K 0.08 to the X and 0.017 to the Y. Once again, if we divide it out here, that's going to give us a 2. The rate constants will cancel. Since these guys are identical, they will also completely cancel. Dividing out our last one there will get us a 2 to the Y. Once again here, Y will equal 1. Again, you take the natural log of both sides and divide. Now that we have the order with respect to I minus, we want to switch it up and keep I minus constant, which would be experiments 2 and 3 would do that. That would keep the I minus constant. So looking at experiments 2 and 3 here, once again, I'm going to put the larger rate up on top. So that's going to be experiment 3. So that would be 4.4 times 10 to the minus 4 equals our K 0.16 to the X and 0.017 to the Y. On the bottom is going to go experiment 2, which would be 1.1 times 10 to the minus 4, I believe. And our K 0.08 to the X and 0.017 to the Y. Dividing this out will give us a 4. Once again, the rate constant will completely cancel. Dividing our first reactant there will give us a 2 to the X. And these guys here will completely cancel. In this case, you could probably again easily see that it is X is going to equal 2 in this case, or second order. Once again, if you weren't sure, didn't have a pretty number, take the natural log of 4 and divide it by the natural log of 2, and then it'll get you there, what you need to do. Now that we have the orders for this reaction, we can actually write the completed rate law, which would be the rate is equal to K times S2O8, try that, 08, and that was to the second. And there our I minus there was to the first in that case. What that also means is in terms of the overall order here, the overall order would actually be in this case 2 plus 1, which would be third order overall. First off, any questions up to that point? At this point, we could solve for K using our completed rate law. And if we rearrange and solve for K, K would equal the rate divided by S2O8 squared, and our I minus, there's a 2 minus there would be good. Once again, we could choose any experiment we want in terms of the values to put in there. So I'm going to, again, just choose the first one. And that would give us our K is equal to 2.2 times 10 to the minus 4 molar seconds divided by our 0.08 molar, which is squared, and our 0.034 molar. So once again, you do need to square it here, obviously, when you're calculating for K. That's going to give us 2.2 to the minus 4 divided by 0.08 squared divided by 0.034, and that gives us a 1.01. Unit-wise, molarity up on top, molarity on the bottom cancel, leaves us 1 over molar squared seconds. The molar squared coming from right there. First off, any questions on any part of that calculation there? Once again, here you can see this one's actually third order, different than the second orders we did previously. And you could also see when you look at the rate constant, it actually has different units. So the units of the rate constant is actually really important. It actually can tell you what type of reaction you're dealing with. Is it first order, second order, or so forth, just by the units that are present. Any questions on how to do any of that there? Okay, we will lay it up there for today.